Hello everyone, uh, myself Vimash Adhikari. Most of us might have learned about the binomial theorem not in the school level but most probably in high school. In high school math, we also learn about permutation and combinations. Now, even if you have not, I will try and explain any new concepts that appear in short. When I first learned about binomial expansion, I simply could not make sense of why the concept of combination, the NCERT notation, appeared in the expansion. And today I'm trying to provide the intuition about why this must be the case. Okay, so consider the following expansions. These two binomial expansions are the most basic ones we've encountered in school, but we either memorized the expansion or multiplied out the a plus b terms with each other for 2 or 3 times. Uh, but to either memorize the formula or to multiply the terms for larger powers is not convenient at all. For example, what would be the expansion of a plus b raised to the power 5? Well, it's not difficult to guess what the terms would be as it follows a visual pattern. You have every possible combination of a's and b's whose powers add up to 5. So these are the terms that would appear in the expansion, but the real challenge is finding out the numbers that show up before them, their coefficients, and how can we arrive at these numbers without having to use the inconvenient methods we discussed earlier. So these are the coefficients, and now we are going to look at a way that would help us to find these coefficients easily. So we are going to talk a little about the binomial theorem. This is what it says. This formula can be applied for all positive integers n. Now, after looking at this formula, what's easy is to plug in the values for n and obtain the expansion. But what is not so easy to comprehend, at least for me when I first learned this, is how the NCR notation appears in this formula. What does NCR even mean? Well, we'll try to first understand what NCR means, but now before that, let's plug in some value of n to show how this formula can be applied. So let's put n is equal to 4. So if you apply this formula for n is equal to 4, we would get this expression. And when we simplify this, what we'll get is this. So this here is the expansion of a plus b raised to the power 4. Now, before diving deeper into this formula, let us talk about the idea of permutation and combination and why combination appears in this theorem. So basically, permutation deals with the idea of arranging a certain number of objects in a certain number of places. For example, if we were to arrange a pencil, eraser and a sharpener, we can try out every single arrangement and come up with an answer of 6. But as the number of objects increases, it is not efficient to do that as well. Even if we add a pen and a ruler to the previous 3 objects, the number of possible arrangement quickly increases to 120. Now for 10 objects, that goes well over 3 million. So the standard notation for permuting n objects in R spaces is npr or n permute R, and it can be computed using a formula that looks like this. Now let's apply this for 5 permute 3. So now we are going to talk about combination. It is what concerns us more in this discussion. Combination, as you can see in the screen, is the idea of selecting items. It does not matter in which order you do so. For example, in a supermarket, if your mom allows you to buy 3 chocolates and you have 10 options to choose from, the total number of different selections you can make is 10 choose 3, and 10 choose 3 can be calculated using this formula, and when we put in the values, we get a final answer of 120. And while choosing the chocolates, it does not matter whether you choose Kit Kat first or Dairy Milk, if at the end of the day both fall under your choices of chocolates. Now that we have got a little background regarding the binomial expansion and also about permutation and combination, we are finally ready for the most important part of this discussion, the connection between binomial expansion and combinations. The way I will explain this is by an example. And once we understand this, the same idea can be generalized for all values of n. So here we have a plus b whole cubed. That's the same thing as writing a plus b 3 times and multiplying them out. So here I've used three colors, green, yellow and blue. Some might call it lime, yellow and cyan, but that's not important for our purpose. So let me first start by multiplying the second and the third a plus b term, or the yellow and the blue ones. I'm keeping in mind the colors as well, because that will help me eventually to explain the whole thing. Now I also distribute the a and b of the remaining a plus b term as well. Then what I'll do is group the like terms together. AAB, ABA and BAA all refer to the exact same term, that is a squared b. The same goes for ABB, BAB and BBA, which all mean AB squared. However, one thing you might have noticed is none of the terms have A's and B's of the same color. That's a very straightforward and a simple observation, but its implication is important. What this observation implies is that if you have two letters from any two a plus b terms, the third letter you choose must come from the remaining third term, as shown visually by non-repeating colors. Now we can make sense of the grouping of like terms in terms of numbers of a and b. For example, the group of a squared b terms can be referred to as terms that consist of two a's, and that also means that the term must contain one b. So if you do that for all terms, this is the result. Now this can also be expressed in terms of b's. Here we go. And you could write the same thing in terms of combination, because as we saw earlier, combination is all about choosing stuff. How many ways are there to choose two a's from three a plus b terms? It's simply 3 choose 2. Similarly, for each term, here's what it would look like. And finally, when we compute this, we get this. So hence our final result of the expansion looks like this. Now before ending this discussion, one more thing that you might have observed is how 3c3 and 3c0 were the same, and similarly 3c1 and 3c2 were the same. Can you infer something from this? Look at a few expansions and you would find that the coefficients of expanded terms are symmetric. Let's start with n is equal to 0. In that case, you would only have one term. So let me show you this. Okay, now for n is equal to 1 is simply a plus b. So 1 for a plus b whole squared is 1, 2 and 1. Likewise, for a plus b whole cubed is 1, 3, 3 and 1, and so on. Now this right here is very interesting if you think of it carefully. We call this the Pascal's triangle, and there are several mind-blowing stuff hidden inside it. Although this is not a part of our discussion, I request all of you to explore this triangle in the internet or through books or through any medium you like. That's it for today. But before signing off, I, on behalf of MIN and myself, would request you to please stay at your homes, stay safe. These are indeed stressing times for all of us. Please follow the COVID guidelines. We very well know what to do to prevent this virus from infecting us, and we need to do just that. So thank you everyone for your time and attention. Goodbye.